Alrighty, good morning everybody. Welcome back to Abstract Algebra. Plan for today, get fit. We're going to prove first isomorphism theorem. As far as office hours go, got my usual hours this afternoon at 2, Wednesday hour 4 class at 2, tomorrow 10 in the morning, 1:30 in the afternoon. And as far as homework goes, don't forget homework 6 due on Wednesday. Questions or comments before I do the joke of the day? Okay, so math major once faced the following question on an elementary. I need to plug in my computer. Ain't that a funny joke? Hold on. Experiencing some technical difficulties. All right. Well, math major was once asked on an exam. You are given an accurate barometer. How can you use it to determine the height of a skyscraper? Student answered, oh, that's easy. You go to the top floor, tie a long piece of string to the barometer, lower it until it touches the ground, then measure the length of the string. Professor, unhappy with that answer, and talked to the student after class and said, well, can you give me another method that demonstrates your knowledge of physics more? And the student says, sure. Go to the top floor, drop the barometer, measure how long it takes to hit the ground. No, that's not quite what I had in mind. Would you like to try again? Okay, says the student. Make a pendulum of the barometer, measure its period at the top, and measure its period at the bottom. Try again, says the professor. Measure the length of the barometer, mount it vertically on the ground on a sunny day, and measure its shadow, then measure the shadow of the skyscraper and do some trick. This is ludicrous, says the professor. Again. Walk up the stairs and use the barometer as a ruler to measure the height of the walls in the stairwell all the way up. Last chance, student. Find where the janitor lives, knock on his door, and say, please, if I give you the barometer, will you tell me how tall the building is? Okay, so back to business. Serious business. So last class, we showed that that if we have a subgroup H of a group G, then H is a normal subgroup of G, if and only if H is the kernel of some group homomorphism from G to another group. So in other words, if H is a normal subgroup, if H happens to be the set of all things going to the identity in the second group for some group homomorphism. And our goal is we're going to prove today that if you take a group G and any group homomorphism phi from G to another group, we are going to show that if you take G and you mod out by the kernel of phi, the set of things going to the identity, that's actually going to be isomorphic to the image of phi. In other words, the set of all elements in G prime that actually get mapped to. Or might use this notation instead. Phi of G, both referring to the image, the set, basically the range of the function phi. So in other words, assuming we have a group homomorphism, we only need to know which elements are getting mapped to the identity in the second group to be able to say quite a bit about what does the range of the group homomorphism going to look like. It's going to be G modded out by the set of things mapping to the identity. So we are going to prove that with the first isomorphism theorem. Or fit for sure. Dr. Gerstel, because it's the first isomorphism theorem, does that mean there's a second isomorphism theorem? There's also a third isomorphism theorem, and there's also a fourth isomorphism theorem. But they're all just kind of special cases of the first. If you have the first one, you kind of get the others for free. And at least one of the others will show up later in this packet. So here we go. We're going to let phi from group G to G prime be a group homomorphism. And now we're going to define a new map, psi, and say that the map psi that goes from G mod the kernel of phi to the image of phi defined by taking a coset of the kernel within G. So we're going to take some coset G kernel of phi. Remember, kernel of phi here being a coset, or kernel of phi being a subgroup, and so G kernel of phi is just going to be a coset of that subgroup. We're going to map G kernel of phi to whatever phi of little g is, and I claim that this map psi is an isomorphism. Which then will give us that G mod the kernel of phi has to be isomorphic to the image of phi. This one's kind of a nutty theorem in that we have two different functions going on. We're presupposing we have some phi, a homomorphism from G to G prime, where phi may or may not be an isomorphism itself. But as long as phi is any homomorphism, we can construe an isomorphism of this form by taking in cosets of kernel of phi in this group and spitting out elements in the range of phi. So keep in mind this is going to be a subgroup of G prime, where we're going to take a coset, little g kernel of phi in this group, and mapping it to wherever phi of G happens to be equal to. And I claim this map psi has to be an isomorphism regardless of whether or not phi is an isomorphism. As long as phi is a homomorphism, our map psi that we've defined in this way will automatically be an isomorphism, meaning it'll be a homomorphism that is one-to-one and onto. All right, let's prove this. So, what do we need to check if we're showing a map as an isomorphism? What are the conditions that we need? Okay?
If it's a homomorphism, if it's one-to-one, if it's opposite.
We need to show that psi is a homomorphism. We need to show psi is one-to-one, meaning if psi of first thing equals psi of second thing, then first thing equals second thing. And we also need to show that it's onto, and that everything in this group has to get mapped to by something from this group, which will be pretty easy to show. We also have another thing we need to show for this particular function, and that we need to show this function is well-defined. Mainly because there's a big question of if we have a coset that's represented by two different elements. So, in other words, if G1 kernel of phi equals G2 kernel of phi, we have to answer the question, must phi of G1 equal phi of G2? I.e., must it be the case that psi of G1 kernel of phi equals psi of G2 kernel? Because I would say it's kind of unclear, just from definitions and such, that if you happen to have two cosets of the kernel of phi that happen to be represented by the same element, meaning if G1 kernel phi generates the same coset as G2 kernel phi, will it have to necessarily be the case that phi of G1 and phi of G2 are the same? I would say that's a little bit unclear and something we would need to prove in order to show that this map psi here is a well-defined function. Like I said, everything good? Cool. So let's start by seeing if we can do that. So first off, I'm going to suppose we have two cosets that are the same. That G1 kernel phi is equal to G2 kernel phi. Keeping in mind, kernel of phi here is a subgroup. It's a set of elements. The set of all elements that happen to map to the identity under E prime. If that's the case, we can say that since G2 which we could always write as G2 times the identity. So that'll be in G2 kernel phi, which is equal to G1 kernel phi. In order for G2 to be an element in this coset right here, what does that tell us about how we could write out G2 as a product of two things? Since G2 has to be an element in this coset, what do things in that coset have to look like by definition? If I were to give you something in G1 kernel of phi, what would that look like? Okay.
Would it have to be something else times the kernel of phi?
Well, keep in mind it's going to just, we want G2 to just be equal to a single element. It's not going to be a whole coset of the kernel. Right?
Is it gonna be like a little g prime times the identity?
I mean, it will be G prime times the identity, for G prime equal to G2, yes. How about if I ask this question? What if I told you that G2 is in G1 times some set H? We've seen examples sort of like this before. What would that tell us about the form that G2 would need to be able to take? If we were to say G2 is in the coset G1 H for some subgroup H. Here?
Wouldn't that be G1 little h?
Yeah, it would be G1 times some little h, where what has to be true about little h?
Oh, it has to be an element of h.
Yeah, for some element little h, an element of big H. Yeah, that's exactly right. If G2 is in this coset, that means G2 has to be equal to G1 times some element within this set. So how can we generalize that to this particular case? We have G2 is in G1 kernel of phi. What would the general form of something in G1 kernel of phi look like? If it helps, you could think about kernel of phi as being equal to our H here. Okay.
Like G1 times K, where K is an element of the kernel of phi, or something like that.
Yeah, exactly right. G2 would have to be equal to little g1 times some element in the kernel of phi. I'm going to do G1K for some K in the kernel of phi. In order for G2 to be an element of this coset, that means G2 has to be able to be written in the form little g1 times something in this set. G1 times little k for some k in the kernel. Cool. Lots of cuz in that sentence. Well, so if G2 is equal to G1 times k, what would happen if I tried to solve this equation for k? What would I end up with? If I try to cancel out the G1 from the left-hand side of this right-hand expression. Okay.
Could it be G2 times G1 inverse?
Close.
G1 inverse times G2?
Needs to be G1 inverse times G2 because you're multiplying, in order to cancel out the G1 from the left here, you need to multiply on the left by G1 inverse. So K would have to be equal to G1 inverse times G2. And so, if we were to take phi of G1 inverse G2, Actually, no, let's not do that quite yet. Actually, let's ask this question. If k is in the kernel of phi, what does that tell us we should get if we were to plug in little k into our function phi? In other words, if little k is in the kernel of our map phi, we should be able to say exactly what phi of little k should be equal to. What would that be, Megan? The identity of which group? The second one? G prime? I agree. You sounded not very confident. I just wanted to make you take.
I was wrong.
Yeah, didn't you? The second one, G prime? Are you crazy? No. Not exactly right. So by definition, since k is in the kernel of phi, that means k has to map. If we take phi of k, that has to be the identity element in our second group. So the identity in our second group is equal to phi of k, which is also going to be equal to phi of g1 inverse g2. And now we can do a little switcheroo. Using the fact that phi is a homomorphism, I'm going to write this as phi of g1 inverse times phi of g2. So here, I can use the fact that we know phi is a homomorphism to split up phi of g1 inverse g2 into phi of g1 inverse phi of g2. And I'll write it here since phi is a group homomorphism. And phi of g1 inverse times phi of g2 gives us the identity element. What is that going to tell us about the relationship between phi of g1 and phi of g2? Okay.
They're inverses of each other.
They're inverses of each other? Oh no. I was hoping to show that they were equal.
Oh, phi of G1 and phi of G2. Gotcha. I thought that the inverse was. Yeah.
So the fact that you can multiply phi of g1 inverse times phi of g2 and get you the identity, if you just multiply it on the left of this expression, both cases by phi of g1, what you would end up with is these are equal to each other. And hence would tell us that psi of g1 kernel of phi has to be equal to psi of g2 kernel of phi. So in other words, our map is well defined. It does turn out that if the same coset is represented, the same coset of kernel of phi is represented in two different ways, with g1 versus g2, in order for these cosets to be equal, it would have to be the case that phi of g1 would be equal to phi of g2, and so we wouldn't necessarily have this well-definedness issue show up. And so in other words, everything is hunky-dory. We know that if you take two elements that are equal to each other in G mod kernel of phi, if you take two cosets that are the same, then the thing that then psi of the two cosets would have to also map to the same thing. Something which wasn't really particularly obvious just by the definition, but turns out to be the case. This map is well defined. Everything is all neato mosquito, as they say. So any questions so far about why this map psi that we just defined has to be a well-defined map? In general, anytime that you define a function that takes in cosets as its inputs, you always have to kind of go through this well-definedness issue of, if I happen to have the same coset that's represented in two different ways, will it necessarily map to the same thing under the function I've defined? In this case, it turns out yes. So we don't have, so everything's okay. We do have a well-defined function in which anytime if A is equal to B, then psi of A is equal to psi of B. But if it's not obvious that that's the case, you do need to go through this sort of argument. Just check. All right, Megan, you mentioned earlier that we needed to do 3 other things to check this as an isomorphism. Can you remind me what we need to check?
You check that it's a homomorphism, that it's 1-to-1, and then it's on.
Homomorphism, 1-to-1, and onto. Which would you like to start with?
Homomorphism.
Good choice. If you had said 1-to-1 or onto, I would have given you another crazy look.
He's probably going to today anyways. So blessed.
All right. So Megan has proposed the correct idea of let's prove next that it's a homomorphism. For the record, you can do these three in any order. The order doesn't matter. I just prefer to do homomorphism before 1-to-1 and onto. So let's check that psi is a homomorphism. So we need to show that if G1 kernel of phi and G2 kernel of phi, this time not necessarily the same coset, if we take these 2 elements in G mod kernel of phi, we need to show that psi of the first times psi of the second has to give us the same thing as psi of G1 kernel of phi times G2 kernel of phi. So in other words, we need to show that if we multiply the 2 cosets together and then apply the map psi, we want to be able to show that that will give us the same thing as if we were to take psi of the first coset and multiply by psi of the second coset. That if we apply psi and then multiply, we get the same thing as if we multiply and then psi. Kind of rhymed. So this is a pretty quick argument, actually. Because if you take psi of G1 kernel of phi and multiply by psi of G2 kernel of phi, what's that going to give us by definition? So what would psi of G1 kernel of phi be, for instance? We just plugged in G1 kernel of phi into the map psi. Elaine?
Phi of G1.
Yeah, that's just going to be phi of G1. Whereas psi of G2 kernel phi is just going to be phi of G2. Can we say that? Can we just combine those to get a single phi of G1, G2? Why do we know we can do that? Yeah, we can use the fact again, we know phi is a homomorphism, meaning it's okay to just take phi of G1 times phi of G2 and get that. But we also know something else about phi of G1, G2. We know that that is going to be equal to psi of G1, G2 kernel of phi. We'll have parentheses. Because by definition, psi of G1, G2 kernel phi should just give us phi of G1, G2. Phi of our coset element representative. And lo and behold, that is in fact going to give us psi of G1 kernel of phi times G2 kernel. Yes, that's the proper number of closed parentheses. So psi is in fact a homomorphism. Because if we take 2 cosets and multiply, then apply psi, we're going to get the same thing as if we just took psi of the first coset times psi of the second. Basically, coming down to the fact that psi has to be a homomorphism because phi is a homomorphism. And okay with that? All right, Megan, what's next?
Let's do onto
Is that weird look I promised? All right, fine, we can do on. Sure. All right, we're going to prove next that psi is onto. Well, first proving psi is 1 to 1, because apparently that's what we're doing.
No.
So what does that mean? So that means we need to show that given any element in the image of G, in the image of phi, excuse me, any element in here, we need to show gets mapped to by something from G mod kernel of phi. So let's start by letting, I don't know, call it G prime. We're gonna say is an element in here. And we want to show that G prime, if G prime is an element in the image of phi, we want to show that then G prime has to be equal to psi of something coming from G mod kernel of phi. So what does it mean to say that G prime is an element in the image of phi? If G prime is in the image of phi, what has to be true about G prime? If I were to tell you I'm thinking of a group homomorphism and 6 is in the image of that, what does that mean to say that 6 is in the image of a function? Or 6 is in the range, in other words. Right?
There exists some x such that phi of x equals g little g prime.
It means that 6 has to get mapped to by something, that 6 is equal to phi of something. And so in this case, if G prime is in the image of our map phi, that's going to tell us that G prime has to be equal to phi of, what did you call it, Line?
X.
Phi of x, I can use G, but okay. Has to be equal to phi of x for some x an element of what? Yes, Line?
Big G.
Yeah. Because in order to be in the image of phi is a map from G to G prime. That means the only element we're allowed to take phis of is phis of elements from the original group G. Okay, so G prime is equal to phi of x. I claim then we can find some element in G mod kernel of phi for which G prime is equal to psi of. Don't tell your English professors that sentence structure. If G prime is equal to phi of x, what element in G mod kernel of phi would G prime have to also be equal to psi of, by definition of how the function psi works? Okay?
X kernel of phi.
Thank you. Yeah, because by definition, x kernel psi of x kernel phi is just going to be phi of x, which we already said is equal to G prime. So psi is onto, in other words. We've shown that given any element in the second group here, we can always find something in the first group that will map to it under psi. And in particular, G prime will get mapped to by psi of x kernel phi, where x is the thing that happened to map to G prime under the map phi in the first place. All right, Megan, what's left?
1 to 1.
1 to 1. Okay. Erase homomorphism. So the last thing that we need in order to show that psi has to be an isomorphism is we need to show that psi is 1 to 1. So our goal, or what we need to show, is that if psi of G1 kernel of phi is equal to psi of G2 kernel of phi, then G1 kernel of phi has to be equal to G2 kernel of phi. That's going to be what we would need to show in order to show psi as a one-to-one function. That if psi of coset 1 is equal to psi of coset 2, then coset 1 has to be equal to coset 2. All right, here we go. So first of all, we could say that if psi of G1 kernel of phi is equal to psi of G2 kernel of phi, then it would have to be the case, by definition, that phi of G1 is equal to phi of G2. And using the fact that phi of G1 is equal to phi of G2, we should be able to know from that that G1 is equal to G2, right? Why? Give me some weird looks.
I think you can't do that.
Why not? I just did.
We only know that phi is a homomorphism, not that it's not homomorphism.
1 to 1.
Yeah.
Oh my gosh!
Oh, my
We only know that phi is a group homomorphism, so we can't say phi of G1 equals phi of G2. We don't know that. G1 has to be equal to G2. So I'm going to erase that. Sorry if I'm ruining your notes by trying to trick you. So we can't necessarily say from this that G1 and G2 have to be equal because we don't know if phi is 1 to 1 or not. If it is, then yeah, G1 has to be G2, then thus these two cosets have to be the same and we're done. We can't determine from this if G1 and G2 have to be exactly the same element. Because if phi is not 1 to 1, then they don't have to be. Fortunately, we don't need to show that G1 equals G2 necessarily. We just need to show that G1 and G2 generate the same coset of the kernel of phi. Because if we can show that they generate the same coset, then we're home free, even if we don't necessarily know that G1 has to equal G2 itself. So we know phi of G1 is equal to phi of G2. So we can't necessarily say G1 equals G2, but we can say that the identity in the second group has to be equal to phi of G1 quantity inverse times phi of G2. Because if we were to multiply both sides of this equation on the left by phi of G1, we would just get phi of G1 equals phi of G2. Oh, sorry. And so, or equivalently, if we were to multiply the left-hand side of this equation on both sides by phi of G1 inverse, on the left we'd just get the identity in the second group, on the right we'd get phi of G1 inverse times phi of G2. Which, using again the fact that phi is a homomorphism, we know that's going to be equal to phi of G1 inverse G2. And if phi of G1 inverse G2 is mapping to the identity element in the second group, what does that tell us about G1 inverse G2 if phi happens to map it to the identity? In particular, that's going to tell us that G1 inverse G2 has to be an element of some particular set. And which set is that going to be? Peter?
Is it the kernel?
Of?
The kernel of phi.
I'm making you specify because we have two different homomorphisms flying around here. Yeah, that's exactly right. Since G1 inverse G2 maps under phi to the identity element of the second group, so let's say the identity of G1. Since phi of that thing maps to the identity, by definition, that means G1 inverse G2 is in the kernel of phi, which in turn is going to imply that G1 inverse G2 is equal to K for some K an element of the kernel of phi. Which in turn is going to tell us that G2 is equal to KG1. No, G1K, because if we multiply on the left on both sides by G1, we'll get that, which is going to be an element in G1 times the kernel of phi. And if we know that G2 is an element of the coset G1 kernel phi, what's that going to tell us about G2 kernel phi and its relationship to G1 kernel phi?
They have to be equal because if you have anything in common, you have to have everything in common.
Bingo. We know from the fact that G2 is also going to be an element in G2 kernel phi. We have two cosets of kernel phi that have a single, at least one element in common, G2. And as we've seen before, when it comes to cosets, if two cosets have at least one element in common, then they must be exactly the same set of elements. Since any two cosets either have to be exactly equal to each other, bless you, or they have to be disjoint, meaning they have no elements in common. And that's what we needed in order for psi to be 1-to-1. We showed that if psi of G1 kernel phi equals psi of G2 kernel phi, then G1 kernel phi equals G2 kernel phi. And psi is 1-to-1, and since psi is 1-to-1, and since psi is a well-defined function that is a homomorphism that is onto and 1-to-1, thanks for giving me the weird recorder again, Megan, that's enough to then tell us psi has to be an isomorphism. Big conclusion from all this, psi is an isomorphism. And we are golden. Any questions or comments? In general, you typically in practice don't use the first isomorphism theorem by defining this specific map psi. What's going to be useful for us is more this property in general. It's just going to be knowing that G mod the kernel of a homomorphism phi has to be isomorphic to the image of that isomorphism. And knowing that is going to allow us, knowing that is going to allow us to prove some interesting groups are isomorphic that would be difficult to show otherwise. So let's look at an example where we actually show two groups are isomorphic using this chart. Everyone okay if I erase this right hand board? Stop, tell me to stop or forever hold your peace, okay. This is arguably, by the way, the most important theorem we've proven all semester. I'm going to say arguably because there's some other pretty big powerhouses like the Granges theorem, fundamental theorem of abelian groups, good old FGAG. Fundamental theorem of cyclic groups are also pretty high up here. This theorem gets used so much in abstract algebra. And the reason why it gets used is basically it gets used to prove that if you have a quotient group, you can show your quotient group is isomorphic to something that's not a quotient group. And because quotient groups are kind of hard to work with, you may have noticed, being able to say, oh, I don't want to prove things about quotient group. I'm just going to prove something about a group it's isomorphic to that behaves much more nicely is going to tell you the same sort of properties have to hold true in the original group. Let's see if we can find some fun isomorphisms in this way. So as an example, I'm going to flip the page in the packet. I'm going to prove that if H is a subgroup of non-zero complex numbers under multiplication, satisfying that a squared plus b squared is equal to 1. You all proved on homework 2, I think, that this is going to be a subgroup of the non-zero complex numbers under multiplication. I claim that if we take the non-zero complex numbers and mod out by h, that's going to be isomorphic to the group of positive real numbers under addition. And if we take the set of all complex numbers, mod out, or non-zero complex numbers, mod out by h, we're going to get a quotient group that's isomorphic to the group of all positive real numbers under multiplication. So there's two ways we can do this. We can either try and explicitly construct an isomorphism from this quotient group to R plus. But that's hard. We just spent the last 40 minutes literally doing that. And it was hard. Prove it, take constructing thing, proving its isomorphism. Yuck. So here's what we're going to do instead. We're going to be sneaky about it, and instead of finding an isomorphism going from this quotient group to R plus, we're instead going to find a homomorphism phi that goes from non-zero complex numbers to R plus, and we need a few things. First thing that we need is we need that the kernel of phi is equal to h. We're going to need that because we want to say something about C star mod the kernel of phi, and so we'd like that to be h. We'd also like for phi to be onto, because we want it to be the case that the image of C star, the image of our map phi, has to be equal to all of R plus. Why do we want that? Well, that's because the first isomorphism theorem would then tell us that G mod the kernel of phi would have to be isomorphic to the image. But if we knew that the kernel of phi is h, then the group on the left would just be G mod h. If we knew that phi is onto, that would tell us this group on the right is going to be R plus, our group. Instead of saying G, we have a specific group. Let's say C star. The first isomorphism theorem will tell us automatically C star mod the kernel of phi has to be isomorphic to the image of phi. Well, if the kernel of phi happens to be our group H up here, and if the image of phi happens to be all of R plus, then that would then tell us that we would get the isomorphism we want for free. Meaning there would be nothing left to prove. So in other words, all that we really need to do, we don't need to find an isomorphism directly from C star mod H to R plus. Instead, if we can find a group homomorphism from C star to R plus, which is a lot easier to do, because we don't have to worry about defining a map phi that takes in cosets and other such shenanigans. If we can find a homomorphism from C star to R plus, whose kernel is our group H, and that's also onto, meaning every element in R plus gets mapped to by something from this group, then the first isomorphism theorem would automatically tell us the thing that we want. Because first isomorphism theorem tells us, hey, C star mod the kernel has to be isomorphic to the image. Well, if the kernel happens to be H, and if the image happens to be R plus, then it would give us exactly what we want. So let's see if we can find homomorphism that'll do that. So we need a function, phi, that will take in a non-zero complex number and spit out a positive real number. And we want it to be the case that if we take in phi of a plus bi, we're going to get some real number. And we want to define our map phi in a way that the only things mapping to the identity of R plus are going to be elements in H. By the way, what is the identity element in R plus? The group of all positive real numbers under multiplication. What positive real number, if you multiplied it by anything else, would give you the other thing? Or?
1.
1. Yeah, so the identity in this group is 1. So whatever our map phi does, we want the set of things that are mapping to 1 to precisely be the elements in H. We also want phi to be a homomorphism. And we also want it to be the case that phi is onto, meaning every positive real number gets mapped to by something, by some element of C star. Any ideas as to what a map phi could be that would do all those things? I think the easiest way to think about it is, how could we define a map phi on A plus bi such that the only elements that would map to the identity in the second group, so 1, the only elements mapping to 1 would be elements in this set. Yeah, right?
Just do the square root of a squared plus b squared.
Square root of a squared plus b squared? Okay. Like that? So then your claim is that that would give us a homomorphism such that the kernel would be precisely H and would also be an onto function. Put that to the test. I really want to do this. Sure, I'll do it. Hey, Megan. We have a bunch of things we need to check. Shouldn't have spoken out for the first time about what we need to check earlier. What would you like to check first? We need 3 things. We need, first of all, that phi is a homomorphism. We need that its kernel is H, and we need that it's onto.
Kernel is H.
Kernel is H. All right, we're starting in the middle again. So that's one thing that we need. So kernel phi is, by definition, it's going to be the set of all non-zero complex numbers such that phi of a plus bi is equal to the identity, which is 1, which will be the set of all a plus bi and the non-zero complex numbers such that square root of a squared plus b squared is equal to 1. Oh, hey, that's H. Cool. All right, your function checks out with the kernel is what we need it to be. Megan, what would you like to do next?
He is on.
Phi is onto. All right, we're going to save the homomorphism bit for the end. Okay? So we need to show that phi is onto. Okay? So now we need to show, given any element A in R plus, we need to find some non-zero complex number that'll map to it. Does anybody have a proposal? If I give you an A, what's a complex number that will map to A under this mapping phi? Right?
Just a squared.
Okay, so if we took phi of A squared, that would give us the square root of A squared squared plus 0 squared, which would give us A squared back. Well, that's not going to give us A necessarily.
Just make it A.
Oh! How about that? Yeah, if we take the complex number A, which, but Dr. Gerstle, what do you mean complex number A? A is a real number. All right, fine. Phi of A plus 0i is just going to give us A. And since every positive real number gets mapped to by something, that's going to tell us phi is onto. And then, Megan, what does that leave us with?
If it's a homomorphism.
All right, we need phi is a homomorphism. All right, so if we take phi of A plus bi times C plus di, that's going to give us phi of A plus bi times phi of C plus di. All right, it's a homomorphism. It all checks out.
Yeah.
You okay with that, Lauren?
Yeah.
Good. You can use some fancy complex analysis and say, well, technically, phi of A plus bi is really just the modulus of the complex number A plus bi. And then you use the fact that the modulus is a homomorphism into the positive reals, which you prove if you take complex analysis or something. But I don't feel like going through all that argument. So phi's a homo. Before we pack things up, let me give you a little geometric description of what this map does. Let me do that. We're already 2 minutes over, so let me do that on Wednesday. Elaine, it's your job. Remind me at the start of class Wednesday. I was going to give you a cool geometric description of what we just proved.
Yes, sir.
Good. But there's some fun geometric properties of the complex plane that we can actually show from the expression we just proved. Have a good day, everybody.